about some part and less. So just tell me if I should skip some part.
Yes.
So let's just. So ATSB. So the input edge weighted digraph G and edge weighted W, so the non-negative, and the output should be a Tor that visits every vertex at least once. At least once. I don't say exact once. Okay. This is because this version is equivalent to the one with the triangle inequality, which you have to assume.
So it's equivalent?
Yes, to the one with triangle inequality. Remember, okay, so I will write it in graph theoretic terms, so then you will see, so connected, we want to find a multiset of edges that are connected. Okay, so that's the first constraint. So we should connect the graph, we should visit every vertex, and Eulerian. Okay. This in our setting is that the in degree is equal to out degree. Okay. In the symmetric case, it's just that every degree should be even. Here it's that in degree should be equal to out degree. Once you have such a Tor, right? If you have the triangle inequality, you can walk to Eulerian walk and then shortcut. Okay. And if you want to, if I give this input, I can form a complete graph that satisfies triangle inequality. Just set the weight on every edge to be equal to the shortest path between those two vertices. So it should be a strongly connected graph, right? Otherwise there is no Tor and the problem is empty.
Sorry, how is the first direction of the reduction? How is this version going to give you a Tor in the triangle?
Yeah, so let's say we solve it. Now you find an edge set that is connected on Eulerian. Now you take the Eulerian walk, meaning that there is a walk that visits every edge exactly once. And now when you visit the vertex the second time, you just write the transcript. And when you visit the vertex the second time, just remove it. And this doesn't increase the cost because you have the triangle inequality. That's like you do in Christofides or doubles, even in a double spanning tree algorithm. So now, like on a very high level, what we're going to do is to show a sequence of results, reductions, that we can impose more and more structure here. Okay? And in the end of the day, we will have so much structure, so the problem we can solve using previous techniques. Okay? So today, I wanted to start the first half by, again, talking about these reductions. And then the second half that I didn't talk about at all this Friday, I will talk about how to solve the instance finally, that with structure. And the problem is, I would say that last part is the part that is least clean. So it would be nice, you will see that there's a lot of structure, maybe there's a nicer way to solve those instances. Okay. I guess I don't need to have an example. Or, okay.
You don't need what?
An example of ATSB instance.
No.
Okay.
Well, I don't know if
All right. So now we're gonna explain the first step that we can. Here you're given a general edge-weighted graph with edge weights, right? They could have any form and type. Now we'll use LP duality to give a lot of structure. Okay. So to do that, we look at the linear programming formulation. So X.
you want to say the final result is the approximation algorithm with what?
With respect to the standard LP.
Yeah.
Yes.
Yeah. Right. No, but it gives some constant.
5,500.
That's it. Okay.
Yeah.
Right.
But if you, so now you will see that it's very modular. If you really want to optimize it, you might want to get a couple of hundreds, but it's for sure you will never get close to 2. Okay, so the conjecture should be, so there is a lower bound by Sharikar, Goemans and Karloff. They give a lower bound of 2. So Michel has told me that he wanted to conjecture in that paper that there is a constant, but the other 2 authors didn't want to. And he said, I can even write that I conjecture, but they thought it was not good. But I don't know if they conjectured 2, but let's say that 2 is the right answer. Okay, so XE is the number of times, you should think of this as number of times we traverse E. Yes. So if we have that, right, we want to minimize the sum of xe, the weight of the edges. Then we want to find something that is connected and Eulerian, right? So say that it's Eulerian, we have to say that for every vertex, this is a shorthand notation I will explain. Okay. Okay. So we delta plus for a set S, we note delta plus S the sets of outgoing edges. Okay. And for a vector x and a set f of edges, we denote xf to be the sum of edges in fxe. So this is just the sum of edges going out of V, the values of those. And that should equal delta minus V, which is the set of incoming edges. Okay. So here we just say that the sum of fractional outgoing degree should equal the fractional incoming degree. So it's Eulerian. And then you have the connectivity, which is called the Subtour elimination constraints. So for all the subsets, we have x delta s is greater or equal to 2. Okay. So here you would imagine, like many people write plus and 1. This is equivalent because of these constraints. I don't know what we did it like this for historic reasons. There is no real reason. Okay, so that's our relaxation. So now you can also look at the two previous approaches.
So delta is the sum of plus
Yes.
and minus.
Yes. Yeah. This is all. Think of the graph as undirected. So now we should enter and exit each set. So now, like the previous approaches that was known, you can think of, this polytope is interesting in some sense. If you drop all these constraints, then it's easy to solve, right? It's easy to find an Eulerian vector. Even with the greater or equal to 1 here, it's a cycle cover. And here, if I drop these constraints intuitively, I just want to enforce connectivity. So I could find a spanning tree. And the two approaches that have been known is based on dropping this completely, repeatedly find a cycle cover. You need to repeat log base 2n steps. Shrink the contract.
And that gives
Logarithmic. The best known using that approach is 2/3 log base 2n. So log base 2n is the Friis paper from '82. The 2/3 is from 2007. So here, the other one is spanning tree. So that's the case of Friis algorithm, right? In the undirected case, you find a spanning tree. Now there's always a matching of the odd degree vertices, of course at most opt over 2, so you get a free house. So it turns out in the directed case, a spanning tree can be extremely expensive to correct the parity on. So you need something called, they write in a sufficient condition in their paper from 2010 called fin trees. This is Subtour, so that's the Subtour, Goemans, Madri, Ovesgaran, and Saberi. So that's 10. So they introduced this approach with fin spanning trees for TSP. And they gave a log and over log. So that was the first asymptotic improvement. Okay, and further pushing this approach, very impressive paper by Ovesgaran and Nimanari, right? They gave a upper bound integrality gap that is polylog log n. Okay. But this will use a generalization of Caddy-Singer, so we don't know if this is an efficient algorithm. But it gives you a hint, that this is a good LP. So that was in 2014. So that was Nimanari and Ovesgaran in 14. Okay, so that was basically what the best known results for the general matrix. Okay, so that's our LP. Now we will solve it, but I want to have some structure, and I will get some structure by looking at the duality. Okay, so we should write down the dual. So let's do so. Okay, so this is the primal, this is the dual. So we have a variable for each constraint, right? So we have a variable for each cut. Those are the only ones appearing in objective because the right-hand side is 2, right-hand side is 0. So we will have a maximization problem, which is if I sum up over the sets, 2 times ys. the coefficient on the right hand side. And then I will have a so this is my variables ys here, and then I have a vertex potential alpha v corresponding to the quality constraints. Now, in the dual, right, we have a constraint for each variable in the primal. So for every edge, okay, we will have alpha u, the tail potential of, so this is an edge, right, going from u to v. So the tail potential minus the head potential plus all the sets that cuts this edge. So all the sets S that cuts this S, plus the sum of S such that E is in delta S. Ys is at most the weight of this edge. Okay, so that's the constraint we have in a dual. The Y's are also non-negative. Okay. Okay. So, so let me state a lemma on the structure of the dual. All right, so lemma.
You're the only guy calling now.
So old lemma. This has now been used. I think the first time I've seen it for TSP was in the primal, but they used uncrossing. That was by Cornelius and others in '85. But what we will say is in the dual, so the exist optimal dual solution y alpha. Actually, you will see that if you were here yesterday, somehow the concepts are similar. So we first worked in a bipartite, and then we see the contractions and the lifts. So I don't know if that seems weird, but it turns out that it's similar. So exist optimal dual solution y alpha such that the support of y, so L equal to the cuts that the dual signs non-zero value to is laminar. Okay. So we can uncross the dual.
So the existence should not be enough, right? We should be able to actually efficiently get such dual solutions.
Yeah.
And so you can do it efficiently
Yeah.
from any dual solution.
Yeah, it's a fun story. So we did it with using like complicated ellipsoid. But then Laszlo asked Anders Frank, and then some guy had done it in the 80s or something. So basically the result is the following. Suppose you solve find an optimal solution to the dual. Right? You can do that in polynomial time.
Which you can do in polynomial?
You can find an optimal solution to the dual.
This because this is just a few. Oh, you have exponentially many variables, but
Yeah. You solve the primal using ellipsoid. Yes. This is just a cut separation. And now you have like, if you run ellipsoid, right, you get polynomially many constraints in the primal. So you only need to consider those variables in the dual. Now, I think it was in Hungary, I don't know the name, but he showed that if you're smart in the order you choose the uncrossing, it will terminate in polynomial time. Another way is just to run ellipsoid. But yes, you can find this in polynomial time.
So again, this set L or whatever is
The support of y.
the support of y is laminar.
Yeah.
But that you didn't explain it. This is this is a black box for us.
Yeah. I can prove it.
Yeah. But it's what's the intuition? Maybe you can just.
Yes, take an, I think proof sketch. Let me see here. Take an optimal dual solution that minimizes sum of S, ys. Okay? So out of all the optimal dual solutions, take the one that minimizes this sum. Now, suppose that this dual solution contains two sets that cross, contains A and B, okay? Then I can instead take a dual solution where I take, A prime and B prime, which is A prime is equal to A minus B. Okay? So basically I decrease A and B a little bit, increase these a little bit. Notice that this maintains the optimality in this objective function, but improves this objective function. So that would be a contradiction. That's the proof. Proof sketch. So
It's a very general principle, right? I mean, it probably
yes.
works in lots of situations.
Yeah. So
Is there a characterization when such cut constraints or set constraints are laminar?
yeah. If there is a I don't know.
Yesterday we saw one, here we see one. It's a natural question.
Yes.
Yeah, when are the...
It's a good question. I don't know if there's like a clean characterization. But there is an interest, like the observable network design algorithms by Jane, where you are given a graph and requirements between vertices U and V. Like it could be an integer requiring the number of paths you should have between these vertices. Then the only algorithm we know is to uncross the primal, show that there is a variable of value at least 1/2 and do iterative rounding. So there is like no other versions of those two approximations.
By the way, this immediately doesn't seem to be efficient, right?
Yeah.
This
was an existence proof.
This is an existence.
Yes. But as I said, yeah. Let me not go into that. I don't even remember the ellipsoid, but there's an Hungarian that solved the problem for us. Okay. Okay. So we have a dual solution, optimal solution, that is a laminar family. Okay, so that means that our graph, somehow we have a graph, right, and we have sets with some positive values. So we have value 1, 4, 5, 6, 4, 3, for example.
So these are, that's y-axis.
Y-axis.
You assume they are integer.
Yeah, sorry, yes.
Yeah, that's okay.
Yeah. 3.4. Yes, it's a good point.
These are rational,
Yes.
but you can make them integers.
Yeah, I don't know. I don't.
Not is scale or
Opa.
they are rational.
Yeah. Yes.
So this is a structure you can uncover in polynomial math.
Yes. So now, if we take optimal x and y alpha of that form that is laminar. Okay, so we have an optimal primal and dual solution, right? Now you know from complementarity slackness. So by complementarity slackness, okay, the primal complementarity slackness says that if xe is chosen by the LP, then the corresponding dual constraint should be tight. Okay. So that implies, so let me call this uv. So this implies that alpha u minus alpha v plus the sum of this ys is equal to the weight of this edge. Okay. And dual complementary slackness says that if ys is positive, then this corresponds to a tight constraint. So this says, we have a dual solution and a primal solution. The weight of our edges is defined by the node potentials plus the number of, plus if I have a vertex here, u and v, if I have an edge there, right, it's the node tail potential of u minus the node potential. Now it's plus, the weight is now 3.4 plus 4 plus 6. Okay? So the dual defines the weight function in some sense. We will forget about w and think of it as the dual defines a weight function. And each set here is tight, meaning that there is one unit of flow going in according to x and one unit going out. That's the second constraint. Okay. for every set in L, in the support of Y. So now I want to get rid of the node potentials. Notice that I have the weight of this edge was the node potentials plus the cut. Okay, but let me just define. I can move this equation here. I can move the potentials to the right, right? So I can write that the sum of sets cutting this edge ys is equal to the weight of the edge minus alpha u plus alpha v. Okay. But now I can just define a new weight function by normalizing with the node potentials. So I will define w prime as being the old weight function minus the tail potential plus the head potential. Okay, so now the fact is, or the observation, let's say, observation for any Eulerian vector z, we have that the sum of the edges ze times weight of e is equal to the sum of the edges ze times the normalized weight function. Okay, so why? Any Eulerian vector, you can think of it as it can be composed as a cycle, but these potentials, then you have incoming one and outgoing one, so they will cancel out. Each guy will once appear as an incoming edge and once as an outgoing.
So I have a silly
Yeah,
question.
yeah.
So these normalized weights can become negative?
No, because these y's are non-negative. So it's a feasible dual solution. Yeah, otherwise.
Yeah.
So this is the advantage by looking at this, I think, instead of equal to 1. So we wrote the LP using this version. Sometimes you see this equal to 1 in the complete. Then it's not as nice. So somehow implicitly we're using that we have we are looking for an Eulerian set and not a Hamiltonian cycle. Okay, so now I claim we have a lot of structure, and we call this laminar weighted instances. Okay, so instead of inputted edge-weighted digraph, oh, sorry, I forgot to say, I solved the LP, right? I drop all the edges with 0 LP value.
Sorry, say again.
Yes, I solve the linear program. I have an optimal solution x. Every edge gets a 0 value, I just drop from my graph. So I assume every edge in G has a positive x value. Why can I do that? This does not change the LP value, right? Because it didn't use it. And if I find a Tor in a smaller graph, it's a Tor in the bigger graph. So as long as I only worry about approximation guarantees against the LP, this is without loss of generality. Good. So definition, laminarly weighted instance is a tuple G X, no, yeah, well, I don't know, G L X Y such that G is a strongly connected digraph L is a laminar family of vertex sets. Okay. And for every S in L, right, we had that. Okay, so sorry, X and Y are primal and dual optimal solutions here. Well, that they're optimal will become clear how we define objective function, because we let the dual define objective function. So for every set in my lambda family, the LP test should enter once and exit once. And is this all? Okay, the implicit weight function is the weight of an edge simply the sum of s such that E is cut by delta s weight of y of s. Okay. That's what we had by this reduction. So basically my input now is defined by this lambda family of some weights on y, and the edge weight of an edge is just, in this case, 4 plus 3. Okay.
So
Yeah.
why is that?
Yeah, y, yes. And also these guys are tight, so x is a tight solution with respect to this. So there's 1 unit of flow going in and 1 unit going out of these days. So notice now we forgot about w in some sense. It's an implicit weight function. It's completely defined by the dual solution. And we forgot about the node potentials.
Why
Yeah.
is it clear? Okay, maybe it's simple. Why the lambda family also has to be somehow strongly connected. Otherwise, there may not be any Eulerian subgraph there, right?
The lambda family has to be strong. What does that?
You produce a new instance. I'm saying, why is that instance strongly connected?
Ah, so you mean by we drop edges?
Yeah.
Oh, because the ALP is feasible. So there is always, you can always send 1 unit of flow from every pair of vertices. Think of this cut constraints. It guarantees that take any pair of vertices, U and V, there's 1 unit of flow. So it has to be strongly connected. Yeah, so the LP, at least the text strongly connected. So it's good. It's a good start, otherwise I think we would have a problem.
So it's not really a flow, it's a flow. The x's are not a flow.
Yeah, but they support, sorry,
So
X
there's
support,
superflow,
yes.
it's, yeah.
If I look at X as capacities, I can send 1 unit of flow. At least 1 unit. So that's the first reduction. So now you can just forget about everything I told you, and we assume that we are working on this kind of instances. Okay, so that was basically known. It was not.
Are all edges between, there can be an edge that cuts several sets.
Yes.
And then you add all the sets
Yes.
in the,
Yeah, so 5. Then it will be 5 plus. And interestingly, if there is edges going both directions, they have the same weight. But the graph is not complete, right? We dropped edges. So, but if the ALP decides to keep both edges, UV and VU, in this normalized weight function, they will have the same weight.
And if some vertex is not in any set, then it's in a set by itself.
Some vertex, yes. I mean, some vertex can, yes. You can have a singleton.
Singleton, but it does, is it always?
No, it might not be part of any set.
So then its weight is 0 if there's an edge limit?
If there is edge between 2 of these guys, then it would have weight 0. But if it goes like that, it would have weight 3. Yes. That, for example, happens if you give as input like a tree, binary tree that is connected to the root. It will like put the node potential so that every weight goes to the leaves, the LP. So, okay, so let's now look at the second reduction. That is a little bit more novel, let's say. So notice here, I was insisting on that the in and outflow of each vertex, or of each set, is 1, right? So this means that if I contract this, normal graph contraction, I will get a vertex whose in and outflow is 1. I will get a new laminar weighted instance. Okay? So this gives us some method of hopefully devising a recursive algorithm. Let's say we could contract the set S. This is a smaller instance if I contract like a non-trivial set. And then find a torn smaller instance, then we call it lift it back to the original instance. Okay? And we will see that this always works if the contraction leads to a decrease in the LP value. Okay? So I will define the contract, and then we will say an irreducible instance is an instance for which there is no set for which a contraction will lead to a decrease in the LP value. So we will reduce ourselves to something we call irreducible instances. Okay. So contraction. So here I think I have an elaborate example, so let me check. So this is my set S. Okay, so this is my instance. I on like weight 5, I weight 2, I weight 1, 2, 4, and 3. For example, if there's edges between those, they have weight 0 between these two. Okay, so that's the, I didn't write the edges of outside, okay? So now I contract S.
Which one? The S? Or
The S, the big one in the middle. I do the normal graph contraction, right? So I just replace big S by a small s. Everything else outside is untouched. All right. So this, I claim that everything is like easy to define, right? G is a digraph. L is a laminar family of vertex sets so that every set S is in a tight, right? The only thing we have to worry about is that it's not clear what Y value I should put on this guy. We replaced a lot of Y value with a single vertex. Okay? So to understand that, let's look how we're going to use it. So we're going to use it recursively, right? So we will, suppose you solve this instance recursively, the contracted instance. It's a smaller instance. So I will find Subtour. Maybe it looks like this. Okay. Okay, that's my tour. So you know, I draw it in, you could think of it, I fix an Eulerian walk. I start here, I walk this, I number the edges. Now I want to turn that back into a tour in our original instance. Okay, how can I do that? Well, a natural approach is to just repeat the tour. So you know, I start here, I take that edge. Maybe that edge is this edge, okay? And then I just repeat the walk outside. That's the same. Okay, so now let me use another color. So red. So I enter here. Let's say I enter here. But then, you know, I exit maybe here. Okay. Then I repeat whatever I did out here, and I.
when you say recursively, you solve the contraction, but what do you know? You didn't say what you do inside S.
Yeah, that's the whole.
Yeah.
Yes. So now this is not a tour. We can observe because the red. I mean, I will not be greedy. I will be happy to even have a subtour. Meaning that I have an Eulerian, one component that is Eulerian, but I don't visit every vertex. So the problem is right here, I enter, I need to connect the two dots, the red dots.
The way you enter, if it is not defined.
So it is defined if you fix the Eulerian walk you make. So that's why I said I fix the way I start here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then there is a ordering of the edges. So then these are the consecutive edges in that order. But it's true that there could be manual layering walks, and then you will get different peerings. But let's fix one. So now we have to connect the dots, right? And we do it in the simplest possible way. We add the shortest path between this guy and this guy inside S. So add the shortest path. Yeah, maybe I don't need to.
It has to be connected in itself.
Yes. Yes, yes, yes. So I add a shortest path here. Maybe it looks like that. Okay.
So shortest path will be
With an S. You could take any shortest.
Here.
Oh, okay, I found. Thank you. So you know you could take any shortest path, but for notation convenience, take it inside S. Yeah, if we took any shortest path, then there exists a path because there is. But it's not clear as I was saying that why should such a path exist that if I stay inside S. All right. So there's two different proofs of this. So I didn't prove that in the talk. So let me, that there is this path. Yes. So actually, it has a very nice structure S, because it's a tight set. So let me give you the whole nice structure, then it will be clear that there is such a path. Oops. How do you never write on that one?
Well, you can, but why don't you, I mean, if you're not going to use the bar, no.
Ah.
Yeah, just erase what you want.
Okay, well, I can write here maybe.
You can, but what's the advantage if you're not going to
Okay. It's very complicated.
If you want, all right.
Okay, we know this. All right. So let's look at S. Okay, so let's look at the strongly connected components of S. Okay. So S is a tight set, right? X has 1 unit of flow going in and 1 unit of flow going out. So let's look at a topological, or consider topological order of strongly connected components of S. Okay. Consider, let S1 be a head component, meaning that, okay. So now what I mean here is like, just restrict your attention to S, induce on the graph S, and look at the strongly connected components of S. So now we have S1 is a head component. This means that the only edges that can come into S1 comes from outside. There could not be any edge, then it would not be a head component by strongly connected. So S1, okay, but this is a set of vertices. So by the LP feasibility, right, we have X delta minus S1 is at least 1. But there's only 1 unit going in, because S was a tight set. So all the edges have to go into S1. Okay. From outside. Because otherwise this could not be satisfied. Because S is a tight set, right? Okay. So now this means in particular there's only one head component. Now let's look at the head component after removing S1. So let's look at S2. Okay. Again, you have this for S2, right? But now, you know, the only incoming edges to S2 is the outgoing edges from this. Okay. So this means we call it, this has a very nice path structure. Just repeat the same argument. So you have just set S. If you look at the strongly connected components, you have S1, S2, maybe you have L components. You have all the incoming edges going into the first strongly connected component. Then you have like edges into consecutive layers. And here you have all the outgoing edges. All have weight. Yes, incoming and outgoing, the fractional value of the flow is 1. Yes, yes, exactly.
Across every one of these steps.
Yes. So this in particular means that I entered here, right, on this vertex.
So you might as well assume it's one strongly connected
Yes.
component inside there.
Okay, there is some complication, but for the talk, let's assume it's one strongly connected. But yeah, because basically we see, right, if I take the lift here, this red path has to visit every strongly connected component. So basically it reduces to having only one strongly connected component. Okay, so now we know that the red path exists and the blue path exists. Okay. So now I will set the value of this contracted vertex.
But just if it was one strongly connected component, you could solve also recursively inside this.
But we will do recursively inside the strongly connected components here.
Yeah.
Yes.
So there's a separate instance which is also small.
Yes. Perfect.
Only that's not a cycle. It's
Yes. Very good. I will come. Very good. So we have to be a little bit careful. We do some inducing operator that is preserves, because as you say, this is not.
Connect it from the outside.
That's exactly what we do. Okay. Okay. So we solved the problems. So
Early lunch.
yeah. So we have the red guys, right? So now I want to put, what should I put the value of ys to? I set. Okay, so yeah.
Just a question. So why shortest path? I think in my head you can't want the longest.
So longest path is MP hard.
Yeah, I know. So but
You want
shortest
to
is.
be cheap.
Yeah.
But you want to cover as many as.
Yes.
Cover it recursively.
Yes, we will see. Because the way I will set ys to, I want to make sure that the lift, I call this the lift, the subtour here, I want to make sure that the lift is no more expensive than tour in a contracted instance. Yes.
So any path, not the shortest would work. In my head, the shortest is the worst.
Yeah.
Probably wrong.
No, it's a good intuition. So here we are focusing on solve this recursively. Then since I set ys to pay for anything that I do in here, I want ys to be small, because then the value of this instance, remember, okay, so the opt LP value of an instance is just 2 times the sum of ys. Okay? So if I'm able to set the smallest to be smaller than the value of these sets, my LP value decreases. And then I can solve recursively, and I get some budget left to correct whatever I had inside here. So, but then your intuition is completely correct. So why is irreducible instance easy? Because if it's irreducible, the shortest path is long. So basically then it's easy to visit many vertices. Yeah. All right, so we will set ys to guarantee that no matter how we enter and exit, the rewiring we did inside here is no more expensive. So the cost of the red visit, cost of red, if I just look at the set S and the sets instead, cost of the red visit was, right, I traversed the set across the set F, set of value 5, then 2, then 2, 2, 2, 4, 3, 4, 5. I mean, every set I cross twice here in this example. So the cost here will be 2 times 5 plus 2 plus 2 plus 4 plus 3. Okay? So this means that I should set ys should be at least this sum. Because I wanted the tour, the cost the tour pays for that visit, the red visit, is 2 ys. It enters once and it exits once. Okay? So if I would put ys to be bigger than that, at least I would be fine with the first visit. Let's look at the second visit, the blue visit. Well, there the cost is 2 times 5 plus 1 plus 4. It's smaller, so the red guy is the most heaviest here. So if ys was bigger than that, it's clear.
Would it help if you take the sum of
Yeah, if I took the sum, it would be I mean, when I set ys, I want to take the maximum, but then I pay the maximum twice here. Of course, I pay too much here in some sense, because I will not use the fact that I could be lucky that I don't pay the maximum.
Yeah, I understand. I just wonder whether taking the sum
Of all the sets.
of the blue and the red would make anything different.
Yes.
Yeah, it did.
Because, okay, so now I explain it so that if I set the ys to be more than the red cost, I would be fine. Of course, I don't know the red and the blue cost in advance, right?
You could solve this instance earlier.
Yeah. But I will set ys to be the worst possible way of entering an exit. Okay.
But you could have solved it recursively earlier inside that.
Yeah, but the problem is that the tau would depend on my value here that I find here, right?
Inside.
Oh, inside ys I can find a tau.
You can find it. Once you find it. Oh, I see. It doesn't help you. Yes.
Yes.
So you set to the max.
Yes. So ys is the maximum of all the ways we enter and exit. So let me now, there is some important fact here. Because this could, intuitively, this could be very expensive, right? Your path between this red could cross the same set many times, collect a lot of sets. Okay.
So the shortest path is not in terms of shortest path is in terms of the length,
Yeah.
but the cost of the path can be high.
Oh, shortest path is with respect to cost here.
To cost.
Mean cost
Yeah,
path. Mean cost path. So I would say the first fact, okay, cost of LP value never increases by contraction. So this means that the y of the small s is at most the sum of r s r in L by r. Okay. So I will never set ys to be more than whatever I contracted. This is a sanity check, right? If my contraction would increase the value, a recursive algorithm would be not good. We want it to at least not, we want it even to decrease the value. So why is this? So suppose we had a simple case. Your set S had only vertices inside. Okay. Normally, like I want to find a shortest path from this vertex to that vertex. A shortest path doesn't contain cycles, right? You would not have a cycle, then you can remove the cycle. So you will enter and exit each edge at most once. You will enter a vertex at most once. Now I claim that we can always find a path that enters each set at most once. Okay, why? So suppose we have a set S and a set R. Okay, we enter once, we do something, then we enter the second time and we do something. But remember the nice structure, I could just replace whatever I want around by this path. Okay. Because, you know, every incoming could reach every outgoing. So there's no reason to go into a set more than once. Okay. So this means that we can always find a path that has cost at most the sum of YRs. Okay. And this is what, in fact, we think of a mean cost path. We would like to say we think of mean cost paths of these kind of paths that only crosses a set once. Okay. Is that fine? So okay. So now we are ready to make a recursive approach. So we just have to define what we mean by the value decrease. Okay. So definition, a set S is reducible if its construction causes a decrease of at least value of S over 4. So where value of S I define as being the LP value of the set strictly containing S. So this is equal to the sum over R that is strictly containing S. R is in the lambda family, Y are 2 times that. Remember the LP value was 2 times. So I want to have a decrease that is 1/4 whatever is the LP value of the set strictly in S. So when contracting S, I want to have a decrease that is at least 1/4 of the value inside S. So the value inside S here would be 2 times 2 plus 2 plus 1 plus 4 plus 3. That's the sets of inside S contribution to the LP value. I want the decrease to be at least 1/4 that.
The decrease will be 1/4.
Yes. So that's 1/4. I call this the value of S, the LP contribution of the sets strictly inside S. Okay, so now I will show an irreducible instance is just an instance which no set is reducible. Okay. A singleton cannot be reducible because the value of a singleton is 0. Okay. Well, yeah, so more than that. Let's say we increase more than. Yeah, more. All right, so let's now, the theorem is, I guess I can do that here. Let theorem.
If there is such a thing, you still need to analyze the cost of that.
Yes, so let A be an alpha approx for irreducible instances. Okay. Then there is an 8 alpha. Then there is an 8 alpha approx for general instances. Okay. So general instance I mean for lambda weighted, but as we saw, that was the same. Okay, so this means that we reduced up to constant factor from when we prove this theorem, we can focus on irreducible instances for which the contraction doesn't cause a lot of decrease. Okay, so the proof is, okay, I guess it's okay. So the proof is, we give an algorithm, of course, using A. Proof if instance, so we're given some instance, right? If instance is irreducible, simply use A, right? Because, I mean, then we have a alpha approximation, and that's better than 8 alpha. Otherwise, select minimal, so it's a minimal reducible set. That will be important.
Minimal
inclusion-wise. Reducible set. Let's call it S. Okay. So we have selected our minimal reducible set. Well, we recursively find Tor in contracted instance and lift it. Okay, so lift it as I explained here. So now, what is the cost of this? The cost of the subtour we get. So cost of subtour. Well, remember the lift, we defined it so that it would not be more costly than the tour in the smaller instance. So we can cost of the subtour is just the cost at most the cost of the tour in the contracted instance. The cost of the tour in the contracted instance was 8 alpha, right? It's an 8 alpha approximation. So it's at most 8 alpha times the LP value of the smaller instance. The LP value of the smaller instance was the, let's say, opt of the original instance. But now we had a decrease, right? So we got a decrease of at least value of S over 4. Okay, that was the definition of reducible. So this now I can just expand, right? So 8 alpha opt, which is what we want. Now we have a subtour. It might not, it visits everything outside us, but it might not visit everything inside us. But in the end of the day, we would like to find something 8 alpha opt that visits everything, right? But luckily we have some margin to work with. We have a 2 alpha budget, 2 alpha value of S. Okay. So that's the amount of budget we have in order to complete this into a tour. Okay, so now in the talk I gave a simplified proof, right? I said that suppose for simplicity that X, if I just induce on this set S, suppose X is a feasible solution in that. Now I claim it's an irreducible instance because S was a minimal reducible set. So all these guys must be reducible. Okay. So then you apply A, you get a rho times, it's a rho approximation. So you get a rho times the value of S. So you actually are better than you need to be. Right? You're better. Okay? So now, unfortunately, the problem is that the set S, if I just induce on that, X is not a feasible solution. So what we will do is, so instead of inducing on S, we just contract the complement. Okay? So instead of having the set S, so we have the set S, right? It was complicated, it was something like that. Okay, so that's my set S. Now, when I induce on S, normally in graphs, right, you just induce on it. Here, I will remove the set S, I will keep everything else, all the sets, and then I will have a new vertex Y S bar. Okay, and the reason I do that is, right, because here is some edges going out and in, and I want to have a TSP instance. So I need to like redirect these to the complement. Okay. So now I can find a tour. This is an irreducible instance, by the way, because I only have a vertex here, which is reducible, and these were irreducible. So now I can use A to find a tour in this smaller instance. So I will set YS bar to be equal to value S. Okay. So this will be very expensive. This guy has the whole cost of everything inside S. Okay, so the cost of this instance is 2 value S. So with A, I will find something of value 2 alpha value S. Okay.
To show that with this value you have a physical.
Yes. So now this is not a tour inside S, right? We wanted to have a tour inside S. So let's make the simplifying assumption that S was strongly connected. Then every time I found now a tour here, right? I exit maybe many times. But now I do a very similar thing as I did in the lift. You know, if I entered here and exit there, I will add a path here. But again, this path can be selected to enter each set at most once. Okay. So that path will, every time I enter, and every time I exit and enter, I have to patch them together. That will have cost at most value S. But this tour in this instance paid that every time it exited. So that's the proof. Now if it's not strongly connected, you have the path structure, then you just do this inside each strongly connected component. Okay. That was quick, but that's
yeah, but when you put value S there,
yeah.
you could have put anything you wanted. I mean, you need that the X will still be a feasible solution.
Yes, but I want that the tour here is no more expensive. No, the Tor here is at least as expensive as whatever I will get as a Tor inside S.
So you can pick S whatever you want and just show that
Yeah.
just use your alpha approximation.
Yes, exactly.
And then use the fact that this was the value to
Yeah.
count.
Yeah. So I will for sure not be more expensive every time. Okay. So this is, now we can concentrate on irreducible instances. If you didn't follow the last, just think of the case when this was X was feasible. It's just some minor issues. Okay. So I don't.
If you want, you can take a break. It's up to you.
What is the time?
It's just an hour and another hour.
So let's take.
12:30. So it's a natural time. No?
Let's take a break. That goes between two vertices, and there is no set S that it crosses in the laminar family except the singletons. This edge is basically node weighted, meaning that the weight of this edge will be YU plus YV. Okay. So this is intuitively why this is good, and we will solve these.
I thought the YUs and YVs for non. Or it may be in the laminar.
Yeah. Otherwise, they might be zero. Let's say they are zero. So this looks node weighted. So then we will use the techniques for node weighted to solve this. Okay. So let's now.
What was the best result for not weighted?
So that's I think it's 27 approximation.
Some constant.
Yes.
There was a constant.
Yes. Yes. So that was my paper 15. Yes.
Yeah.
So yeah. Yes. Yeah. Otherwise, so now in the reduction we will use the node weighted. Okay. So I want to prove that if we have a good algorithm for vertebrate pairs, then we get a good algorithm for irreducible instances. So theorem. For vertebrate pairs that produces as Tor of cost at most beta times, let's say, opt of the instance plus the weight of the backbone. That implies I think it's like a 64 beta approximation for irreducible instances.
What are you assuming that the cost is mostly times the
Beta, sorry, beta. Let's say P. All right. So we have some because it's a vertebrate pair, right? You're given the instance plus some edge subtor B. So I'm saying produce me a Tor that's at most P times op plus the weight of the Tor. We will see that this is most some constant times op. So in the end of the day, you could say something off, but this will imply 64p approximation for irreducible. So this reduces the task to devising such an algorithm for vertebrate pairs. All right, so here the proof, similar. So contract every maximal set S, okay, to get a smaller instance. So I have some complicated instance, right? I don't know. This now becomes just, singletons. This is node weighted, right? Now I only have singletons in my laminar family because I contracted a maximum there, okay? So node weighted instance. Okay, so find Tor of cost at most 28 times opt. Because I write 28 because it's 27 per epsilon. Okay, so 28 is correct. Here you can use that's we proved before. Okay. So here now we find a Tor here in this node weighted instance, of course at most 28 times optimal. Okay. So now you can lift these back.
Using the backbone.
No, we will construct the backbone.
So
So now I found a Tor in a small instance.
oh, sorry, yeah, okay.
So I want to lift this back, right? You know, traditionally I only had the shortest path here to find a lift. The problem is that to define the backbone, I want to cross all the non-trivial sets. If I take the shortest path only, right, I don't cross all the sets. So now I have to be a little bit smart. So I will do it with a twist. And yeah. Okay. So let's explain this twist by looking at an example. So I zoom in on some set S, right? I will do the same fix to everyone. So remember that every set S was irreducible. So if I look at this, I look into a big. So I have some set S. Okay, so we are entering this set. The first time we enter this set, we enter it through some vertex US. Okay, so this is set S, and we exit through some vertex VS. Okay, but what does it mean that this set is irreducible, right? This whole set is irreducible. So S is irreducible. That means that there is some unlucky way of entering an exit that is very expensive. Okay. They exist US max and VS max, so that if we enter to US max and leave from VS max, then we cross 3/4, at least 3/4, right? Value of a weighted fraction of 3/4 of the sets inside us. Across a weighted fraction of 3/4 of the sets.
When you say we cross, it means every path.
So, okay, so let me explain. So here, let me take, this is US max, and maybe this is VS max. So now I will first add a shortest path from US.
No, but in what you say.
Yeah, I understand. Okay, so now I will add a path, not necessarily the shortest path between US max and VS max, but I will add a shortest path that enters a set at most once. Okay, so there exists such a path, right, that we proved. This has to have length at least the length of the shortest path, because you know. But then, if it has length at least as long as shortest path, we know that it has to cross at least 3/4 of the weighted fraction, because otherwise it would have been reducible. So there must be like US max and VS max, so that if I had such a path, it must cross a lot of its sets. So now you can think like maybe 3/4 is the optimum, or optimal constant, but you could think of having 0.999 here. This means that I would basically visit almost all the non-trivial sets. Even the singletons of value. So now I add some path here. maybe it's like that. And then I add a third path going from VS max to VS. This I only do the first time I visit this set. This is to make sure that my subtour crosses a lot of the non-trivial sets. Okay?
But you get this cost only from on the two parts on the sides. You don't, right? I mean the reason it's long or it's
Yeah.
heavy,
Yeah.
just from these two things, US max and
Yes. Yes.
and VS max.
Yes.
You don't know this maybe.
Yes. We forget about those. These paths don't help us. Is that the point?
No, I thought. So what helps you is what helps you is between US max and VS.
Yes. Yeah. We know that this is expensive. That's all. But this we have to add, right? But this will increase the value. So we had at 28 opt. We add 3 paths inside. So this will increase the value, but most 3 opt. Okay. So now let's call it B has cost at most 28 opt plus 3 opt for these paths we added. Is 31 opt. Okay. Because this guy has cost at most the value of the sets inside here. This guy has cost at most the value of this guy, and this guy has cost the most value. So that increases the cost by 3. Because we only do it the first time we visit this.
It's opt or it's opt-in or the value of S.
Yeah, so here it's value of S, but we do that for every set. So you sum up. Yeah, actually you could forget about the outermost sets, but yeah. So this is not the backbone, right? Because the backbone required to visit every set. Here we have R1 and R2 that it doesn't visit in. Okay. But these carry very small value. In our case, they carry at most 1/4 the value of S. And you can think of it speeding it up, right, so that it carries 0.01 value. Okay. So what can these guys are irreducible, right? So we can just recursively solve these to find torrs inside these guys. Because they are very small. You can always recurse if the value drops a lot. And, these are small values, so we can find torrs inside those. Once we found torrs inside those, we contract to single vertices. And once we have contracted this into single vertices, then B is a backbone. So that's the instance we will apply the algorithm we assume to have. So let me just summarize here. So I contracted the maximal sets. I used the node-weighted algorithm to find a torr in that instance that I lifted back. But the first time I visit a set, I do something strange. And this is to make sure that my subtour crosses a lot of the sets in my lambda family. So I will identify basically the worst possible way of entering and exiting this set. Since it was irreducible, this must visit a lot of the weight of the lambda family. I recurse from the guys that I didn't visit, which is a small fraction, and then I contract them. In this new instance where I contracted all these guys to single vertices, B is a backbone. So if we can find a constant factor there, we are done. Okay. So that's the last reduction.
And by the way, in the sets you construct,
Yeah.
you're running the algorithm recursively, but again, it's not a cycle you want. Oh, it is a cycle.
Yeah, or it's a cycle on a strongly connected components. Yeah. But if we assume them to be strongly connected, it's a torr inside. Okay, so that's the last. So now it remains to solve that. So let's talk about that. So now we can assume that we have to solve these kind of instances, right? You can be a little bit more greedy and say, hey, actually here our backbone visits almost all of value. But let's forget about that and just say that it visits each non-trivial set. And the funny thing is that this is almost node-weighted, right? But it's not exactly node-weighted. So what we will do is to now look into a little bit of the machinery, how we prove the constant for node-weighted, and then we'll adapt that. Okay. But yes, maybe you agree that this looks pretty structured. In the end of the day, actually, if you have 0.99 there, you would guess that you have a subtour that visits basically 99% of the vertices. At least the weighted fraction. Mm-hmm. All right, so let's think of what do we want to do? We want to solve now, we are given an instance together with a subtour B. We want to output something that is a constant times the optimum of the instance plus the weight of the tour. That's the goal. We have reduced our task to that. So in a no-weighted paper, we show a reduction to a problem we call local connectivity ATSB that looks a little bit easier than ATSB, but it turns out to be equivalent up to constant factor. So that's the one we're going to solve here. So let me define that problem. So local connectivity ATSB so you know, ATSB or TSB in general is about finding a tour that visits all the vertices in the graph. Here we will relax that into local connectivity requirements. So in particular, I will give you a partition of the vertices into sets, V2, V3, V4. So the only requirement I say is find me subtours. They don't need to be connected, so that one of them crosses each of these partitions. You only need to find subtours that crosses each of these partitions. Maybe you find something like that, and V4. You know, there could be some vertices in here that are not visited at all. You need to find subtours that crosses this partition V1 to V4.
You want to cross every partition?
Yes.
So there are some you didn't draw?
I crossed each V1. Oh, what do you mean?
Yeah, V2 and V3.
Oh, no, I just want to go out and in for each set. Not each pair, yes. Each pair would be then, that seems hard.
Yeah, you want to go out of everything.
Yes. So now we should measure progress because somehow the subtours are local tours, right? So now, like, you need some measure of progress, like what's a good subtour? It could not be too, yes?
So the partitions are part of the instance of the problem?
Yeah.
Okay.
So yes, so two phases. First phase, fix or compute, you need to do it efficiently, LB V to R plus. So we assign a non-negative number to each vertex. What's the intuition? This is the amount you're willing to pay to visit that vertex. So LBV is amount you're willing to pay to visit V. Okay, so somehow this is like a simplified dual. You know, the intuition where this came about was node weighted. Node weighted has only dual values around the vertices. So in node weighted that makes perfect sense. So we fix LBV to be equal to opt plus the weight of the backbone over the number of vertices in the backbone if V is in the backbone and 2YV otherwise. Okay, so forget about exact numbers here. This will be clear when we do the analysis, right? This is just, you do the analysis and you see what this is. So this is the first phase. You're given the graph, and in our case, we are also given a backbone. You need to calculate the LB. Okay? Opt is the optimum LP value of this instance. So now in the second phase, maybe I explain it. We'll see why I explain it like this, but maybe it's a bad one. So in second phase, okay. Or I finish here. So second phase, given partition V1 vk of the vertex set, output Eulerian set F. So this means just subtours. If you have Eulerian sets, that's a bunch of subtours. They don't need to be connected. Such that each Vi is crossed. Okay? So that's what I said, right? Here is input V1, V2, V3, V4, V5. And our output could be this set of edges that I drew. That will cross all the partitions. Now, F is alpha light if for every component, so every subtour, GT, let's say T, subtour T of F, we have that the total cost of T is the most alpha what we were willing to pay for the vertices it visits. So here, this is sum of all the edges. Here's the set of vertices. So think of the unweighted case. Okay, all the edges have value 1, let's say, and I'm willing to pay 1 unit to visit every vertex, because if it was a Hamiltonian cycle, that would be what I pay. So here, the lightness of this tour would be how many vertices, so how much LB do I collect? 1, 2, 3, 4, 5. So I have an LB value of 5 if I assign 1 to everybody. And the number of edges I have is 1, 2, 3, 4, 5, 6. So the lightness of this guy is 6/5. And the lightness of this is a cycle, so the lightness is 1. So the lightness of my solution here will be 6/5. So, and we say that an algorithm is alpha light if it always outputs well, alpha light solution. Okay, so for any partitioning, you need to output an alpha light solution. So the reason I described in two phases is that the LB function is not allowed to be a function of the partitioning. Okay, so LB is a function of the instance, but not of the partition. So you have to fix one LB for all, and then you
told us how to fix it.
In our case, but you're free to fix it as you want. So, is it okay? So let me.
You didn't explain how to do the second case.
The second phase.
The second phase.
Yeah. So let me explain. Let me first mention something. So, why is local connectivity at TSP easier than TSP? Suppose my LB function just assigns opt to one vertex. So you collect opt, right? So now you can just forget about the partition you're given and just find a tour. If you have an alpha approximation for ATSP, you will connect the whole graph. So you will only have one component, F, and you will collect opt, right? Because you assigned opt. Okay? But now we have somehow distributed the cost and allow ourselves to do a bottom up. So it's a little bit a generalization of the set cover approach. So the theorem we proved is sorry. So. You should have a course in how to deal with.
Some people that cannot solve TSP.
Yeah. Yes. No. Okay, so now.
Probably the whole.
Yes, I guess it's, yeah, well, unrelated. Yeah, I'm not very practical. All right, so now theorem from 2015 is an alpha light algorithm with respect to LB implies an algorithm for finding Tour of cost at most 10 times alpha LBV. Okay, so this just is the total value you distributed on your vertices. So if I distributed opt, this would mean that if you give me an alpha light algorithm for opt, I will get a 10. So basically they show that they're constant factor equivalent.
And this is
Construct.
then, yeah, the LB, we should think of this as an node-weighted problem.
LB is just a way of distributing the weights. So the you can define LB as you want. Here the weight is not the node weighted; it's the general weights. But so also, if your algorithm for local connectivity is be sufficient, this will be efficient. If you're not interested in efficiency, you can improve this to 3. If you're just interested in integrality gap. So that's also why you can get down to a couple of hundred if you have non-constructive arguments. So now, this means that our goal now, notice that the LB value that we assign, well, you know, it's op plus WB, if I sum up over every vertex in the backbone, plus 2YV for all the other vertices. This is at most 2 op plus WB. So if I can give you an alpha light algorithm with a constant alpha for this LB function, then I have proven what I needed to do. Okay. Okay, so we have reduced our task into finding a constant. So I will write. For the explanation I will do a 4 light algorithm with respect to this. So I will explain you how to do it when the partitions are the singletons, when the VIs is the singletons. Okay, because the way to deal with when they're not singletons is not too hard. It's similar to this paper.
But the partition that you will actually get from the reduction was the partition of the sets, these laminar sets that were typed in the.
No, so they are independent.
It's independent.
Independent. Yeah, so they can cross and so on. Yeah, you have to be a little bit careful. Unfortunately, then it would be nicer, I think. So goal, find one light solution. Okay, with respect to our LB in a given partition. So now assume a simple case is the node weighted case. So node weighted case. Weighted case where L only contains singletons. So L doesn't need to contain any L doesn't contain any non-trivial sets. So let's try to solve that. So we don't have any non-trivial sets. It only contains the
backbone is empty.
The backbone is empty. Good. Backbone. Then assume the backbone is empty. Okay, we can forget about the backbone. So now LB is just 2YV on each vertex. It's equal to the node weight of that vertex according to our lambda family. So now we assumed I do the simple case where the partitioning I gave was the singletons, right? So now I need to find a Lorentz set that has degree at least 1 to every vertex, and it should be cheap. Okay. Each subtour should be cheap. Okay, so we do the following. Consider the constraints Z delta plus V delta minus V is equal to 1 if YV is strictly greater than 0. Z delta plus V is equal to Z delta minus V is greater or equal than 1 if YV is equal to 0 for every vertex. So this is just, okay. So notice that X is feasible. X satisfies constraints. Yes. Z. Okay. And this is just a circulation polytope. This is an integral polytope. So take circulation polytope. So this in polytope, which implies that there exists an integral, well, Z. Okay. Do you agree that this integral Z satisfies the connectivity? I mean, basically, my constraint is that every vertex has to have one guy going out. These guys have to have exactly one guy going out, and now these guys can have even more guys. So the connectivity in the singleton case is fine. So now let's worry about the lightness. So claim. So let F be the output. So F contains ZE copies of E, okay, for every edge. So F is our output. So claim F is one light. Okay. Why? So proof. Consider subtour T. Okay. We have the weight.
What are you have the node weights. It's a one light with respect to whatever node weights.
Yes. So weight of T is just equal to, write the sum of edges in T, the weight of the edge. So let me write this UV, which now it's just a node weight, so the weight of this edge is equal to the sum of UV in T, YU plus YV. But now everybody that has a positive value, right, has exactly one edge entering and exiting it. So this is equal to 2 times the sum of vertices in my Tor YV. And this was exactly LBT. Okay, so it's a one light Tor. Okay, so that was clean, and this is easy. That's intuitively why this was designed to make node weighted work. But the issue is, right, this heavily relied on that all the edges in T were node weighted. So now in the general case, the main issue is, in the general case, suppose we had only one set S in a lambda family, right? I can still, if I find a subtour T that is inside S, it's the same situation, right? All the edges have the node weight, so then I do the same analysis. If I find a subtour outside of S, it's the same situation. So the only thing I have to worry about is subtours that crosses a set. Okay. And what I will do is, I will not find a circulation in my original graph. I will find a circulation in a modified graph, and that modified graph is constructed so as to guarantee that if my subtour crosses a tight set, I will intersect the backbone. Okay. Okay. This will be beneficial because I will always add the backbone to my solution, and the backbone will collect opt. But I can always select this circulation. I can take a min weight circulation, of course roughly at most opt. So that's the way I will deal with these Tors, that they will always be connected to the backbone that will collect a lot of LB value. So there will be two cases.
So connect to the backbone means what? Goes through all the backbone?
Yes. So we have the So we have the backbone. It's guaranteed to visit a vertex inside each set. Looking like that. Maybe it visits 2. So any subtor that is crossing a tight set is guaranteed to visit at least one vertex in the backbone. But now, notice that I always add the backbone. So there will be exactly one component contained in the backbone. And that will contain all the subtor crossing a tight set. There will never, because as I have as a guarantee that a subtor that crosses a tight set will always intersect the backbone. So the remaining subtor, so the remaining T, they will all be this type. And those I can analyze as before. Okay. So let me.
So is this a case of one set? There will be one set in the non-trivial set. There will be an intersection with one vertex of the backbone. You pick it up, and if there were many in your
if it looks like this.
Yeah, and there's some recursion still.
Yes, no recursion. But any Tor that crosses one tight set will end up something like that. But then I could have something that intersects the backbone here. So you will, okay. Let me explain how I do with one set, and then you will see how you can do it bottom up. So now I will try to do the same methodology that I want to find a circulation in a graph, but I will not find a circulation on the original graph. I want to have this property. If I have an edge crossing the cut, I need to intersect the backbone. Okay.
So you write a different now.
Yes. Oh, actually, a new graph, and then I just write the circulation. We call it the split graph. That was from the 2-edge weight. This looks like it's not the right way of doing it. You're just waiting to see when will he realize that this.
Have a limit on the frequency of
Yes. All right, so let's look at one set S and identify a vertex V that is part of the backbone. So V is a vertex of the backbone. Okay? And this is a tight set S. Take any vertex outside S. Let's say U here is not part of S. So it's a vertex. We can send X supports. So X supports, if I think of X as capacities in my graph, right? X supports 1 unit of flow. Flow from U to V. So let me maybe take an example. So I have the simplest example would be I have 2 vertices here, 2 vertices here. Maybe this is V. You know, not so interesting, but it will make the point. So all right, so that's a half integral solution. All the edges are half integral. You know, this is U, let's say. If I look at X, it supports 1 unit of flow from U to V. That's the cut constraints. So it's a half integral solution. So this flow would be to send 1/2 unit here along this path, and it will send 1/2 a unit on this path. Okay. What? So notice that. So let this be F. X supports 1 unit of flow F. So notice F saturates the edges going into S. Saturates edges going into S. right? I send 1 unit of flow from U to V. There's only 1 unit of X going into S. So it has to saturate all these edges. Now I will split each vertex into 2 copies. And the reason I do that is that I want to make sure that if I jump on this flow that I sent from U to V, I need to go to V. I cannot exit this flow before I go to U to V. Okay, so and that was unfortunate that so now I will make the split graph. So I split each vertex into 2. So I will have this vertex. I have a square. The square is like this highway vertices. They are designed so that you cannot escape this flow before you hit the vertex V in the backbone. Okay, so here this is not affected by flow, so I didn't need to split it. But so now I have this guy, so circle. Okay, so now I will write the flow. I will send the flow through the square vertices. Until I go to this guy, then I'm allowed to go back to the circle vertices. And here, I will send the flow on the square vertices. Okay. Okay, so the square vertex carries the flow. The only way to go from a square vertex to a circle vertex is through a backbone vertex. And now the other flow just goes in the circular vertices that I didn't touch. It will be okay. So that would be my graph. Okay. Now notice that in this split graph, if I cross this at S, the only way I can go is to hit the backbone. Like I cannot escape. As I said, the only edges from square to circle vertices is through the backbone vertex, and when we exit the set S, we go from a circle vertex. So now in general, you order the sets according to size, and you say that the only way to enter a smaller set is for a square vertex. The only way to exit a smaller set is for a circle vertex. Okay, so you're always guaranteed to visit the backbone. Now in the singleton case, we split the flow into 2 parts. So you have to scale up your z vector, x vector by factor 2 to guarantee that one of them carries 1 unit of flow. But that's it. Okay. And notice that this has weight 2. You can always find such a mean weight flow of size 2 times opt. Okay? So this means that the backbone is always fine because the backbone collects opt. Okay. So that's basically it. So let me finish with saying some nice open questions, in my opinion, or any question. So one is I find interesting. So it's bottleneck ATSP because so bottleneck ATSP. ATSP. So here, given complete graph with distances that satisfy triangle inequality, okay, find Tor that minimizes max. Find now it's Hamiltonian cycle actually. Now it's important, Hamiltonian cycle that minimizes the max edge weight. Okay. This turns out to be equivalent to finding a Tor of bounded degree. So suppose you're getting an LP solution where everybody has degree 1, find an Eulerian Tor of bounded degree. But interestingly, the fin tree conjecture implies a constant for bottleneck ATSP.
So what's the best known again, log?
So the best known is what is known for fin trees. So log n over log n constructively, polylog log non-constructively. So this First, so you know, there is one problem with a log star and hardness, this asymmetric case center. So I thought maybe this is the way to. This was also if you could prove that there is no such Tor.
Under what assumption?
MP hardness, I think.
MP hardness?
Yes, and it's tight. There is an algorithm that is log star. But yeah, so this is a nice. I think this is a nice problem in between the difficulty of fin tree and the bottleneck. Then we don't know of anything better than Christophilus for node-weighted symmetric. Because you could do the same initial structure of the LP in the undirected setting, but we don't even know for symmetric. I guess that's it.
Right.
Thank you.